Chapter number 15, we're going to start with hydrocarbons in use. Crude oil हमारी main source है for hydrocarbons. Hydrocarbon compounds contain करते हैं just carbon and hydrogen. They're usually used as fuel, but they are used as the starting compounds to make many new compounds. For example, on the top of the list, plastics. Hydrocarbon uh, crude oil, actually, which is composed of many hydrocarbons, is actually a mixture of alkanes, cycloalkanes, alkenes, and apart from that, arenes. Arene means compounds that contain benzene ring, maybe one ring, maybe more. Depends on what the compound is. Cycloalkanes are saturated hydrocarbons in which there is a ring consists of three or more carbon atoms. Keep this stuff in mind because we will discuss cycloalkanes from time to time in this book. Now imagine two carbon atoms at the end of straight chain alkane bonding to each other. This would make a ring. The ring starts from three carbons. Basically, it forms a triangle. When there are three carbon, it forms structure like this. When there are four, it forms a structure like this. With five, we form a pentagon. With six, we form a hexagon, a heptagon, octagon, or anything is possible, right? So moving on, cyclohexane C6H12 is an example. Note that cyclohexane does not form the Gillian alkane formula CnH2n plus 2. Instead, they tend to follow CnH2n, which we have discussed before. Now, this is the example for cyclohexane and its skeletal formula, and then cyclohexane and its skeletal formula. We actually bring the crude oil to the surface with the help of oil wells, transported to an oil refinery. The actual composition of crude oil varies in different oil fields around the world. At the refinery, what we do is that we process the crude oil into useful oils. The first step is fractional distillation of the oil. It separates the wide ranges of different hydrocarbons into fractions. We have discussed different fractions in different books. Now, different books may cater it with different fractions, sometimes 8 fractions, sometimes more, sometimes less. So that really depends upon what the book is going to target in terms of syllabus. So we can bifurcate it into different fractions, that's fine. But the most common 8 fractions are something that we did back in IGCSE. Now, the hydrocarbons in each fraction will have similar boiling points. This is carried out in a very tall fractionating columns. The oil-based compounds that are in high demand are gasoline fraction, which provide the petrol to the car industry, and the naphtha fraction, which actually is the starting compound for making many chemicals in the industry. I hope you understand that the top fractions of the fractionating column are usually much more in demand as compared to the bottom fractions. Now, the bottom fractions are usually known as heavier fractions, and heavier fractions are commonly less in demand. Now, I hope you also understand the point that crude oil is a finite resource and we are rapidly running out of it. And as a planet, as a whole, we are actually trying to go with ways that are other than petrol sources. So non-petrol sources are really nowadays very common, and we are gradually increasing our habit towards green energy. Moving on, the homologous group of alkanes. Now, if we could consider the homologous group of alkanes, and if we consider a couple of examples, for example, to begin with, the general formula is CnH2n plus 2. If we consider n is equal to 5, we'll wind up with the formula C5H12, which is the formula for pentane, as given the displayed formula. Now, the book would continuously repeat the type of formulae for your understanding, for your familiarization, which means you need to be extremely vigilant in your paper. Now, if the examiner comes up with a specific type, you need to go with that type. If the examiner does not come up with a specific type, if he goes with a bigger, broader term that you need to draw the formula, then it's really up to you which formula you choose to draw. But most of the time, they either come up with displayed or structural formula, or they explain the term displayed by using the phrase all the atoms and all the bonds. That is the phrase we use commonly to explain what the term displayed formula means. right? They sometimes come up with structural formula, they sometimes come up with skeletal formula. It's entirely up to the examiner what kind of formula he wants students to draw. Now, moving on, all the carbon-carbon bonds are single covalent bonds. Remember, this is sp3 hybridization. When I use the word sp3 hybridization, it means S, px, py, and pz. All three of them participated for hybridization. That's why it's sp3 hybridization. sp3 hybridization also means that we are going to end up with tetrahedral base structure, and usually the angle that sp3 hybridization has to offer, and that is usually 109.5. Okay, so I hope when we use these words, you get to understand that what we are talking about in terms of whisper theory for these substances. This simply means alkanes have the maximum number of hydrogen atom in their molecules. We call them saturated hydrocarbons. Now, the 3D displayed formula would be something like this. Now, I hope you understand that the dotted and the wedges or the straight lines, what do they mean? Keep in mind that straight lines means in the plane, they are actually a part of the plane. So sticking out of the plane, sticking into the plane, or we can call it in the plane, better call it part of the plan, right? So I hope you understand what all of these symbols mean for 3D structure. And that being explained, let's move on to 15.2, reaction of alkanes. Now, alkanes are generally unreactive compounds. We can explain this by a very small difference in electronegativity between carbon and hydrogen. I hope you remember that from the chapter. We discussed it back in the bonding chapter, and we consider this a very small difference. The book literally used the phrase virtually no difference in electronegativity or very small difference in electronegativity. All right. So the atoms share the pair of electrons in single covalent bonds almost equally. Alkene molecules are non-polar. They're not attacked by nucleophiles. They're not attacked by electrophiles. They have no partial positive charges on any of their carbon atoms to attract nucleophiles. Neither do they have the areas of high electron density to attract electrophiles. I hope this is a very good explanation for it. Remember, nucleophiles, and I'm going to repeat it for you so that it's easier for you to understand. Nucleophiles were actually nucleus loving. Why were the nucleus loving? They attracted positive charges. Why? Because they themselves were either made up of negative charges or lone pairs or partial negative charges. All right. So nucleophiles loved something with a positive charge. Since we didn't have any positive or partial positive charges, so nucleophiles won't be able to attack it. All right. Now, in the case of high electron density, of course, that thing would be attracted by an electrophile. Since there are no lone pairs, there are no negative charges, there are no even partial negative charges, so it won't be attracted by anything positive. So that's what electrophiles are actually would stand for. So that's why we keep saying that alkanes are usually the unreactive ones. Now, if I go back to IGCSE, I hope you understand. In IGCSE, we only studied two types of reactions for alkanes. The first was oxidation, and actually, among oxidation, we only studied combustion for alkanes. That's how we are capable of using them as fuel. Back in IGCSE, the second kind of reaction that you studied for it was substitution. It was possible to substitute the hydrogen atoms and replace them with some more electronegative atoms such as halogen. This is we studied back in IGCSE, and we're going to continue with the same pace and with the same kind of reactions for alkanes. Now, if you remember those reactions, they're not going to be a bigger problem over here because we are just going to go in a little bit of more depth for these reactions. But the reactants, the products, the conditions, all of that stuff almost remains the same. Okay, so let's move on. Alkanes do react with oxygen in combustion reactions. They also undergo substitution by halogens in sunlight. These reactions are covered in the following sections. So, starting with combustion. In fact, let's go with the diagram first. Nonpolar alkanes do not react with polar compounds such as water. The hexane is dyed with iodine to make it colored, so it's more clearly visible. The hexane and the water in the test tube are immiscible, and as soon as I say the word immiscible, you should get an understanding that these two are actually bifurcated into two separate layers since they're immiscible. And of course, the water layer, and remember, the layer that is at bottom has a higher density, as we have explained back in IGCSE, that automatically, if you see two immiscible liquids with two layers, one on top, one on bottom, you are going to understand that the one on top is definitely with lower density, whatever that is, and the one at bottom must have a higher density. Now, what we did is that we dyed it with iodine, and hexane itself can be used as a solvent. So that's about it. Okay, so it gives you an idea. Now, remember, back in IGCSE, we studied one more thing that if we talk about alkanes, then C1 to C4 are gases. From C4 roughly all the way to sometimes some books say C14, some books say C16. That's about it. You can call them because different isomers behave really differently. So you can put any of the numbers here, anything in between 14 to 17, and you would be considered correct. Now, they are liquids, some of which are thinner, lighter liquids, some of which are, of course, thicker, heavier liquids. We do understand that up to C10 or C11, we have thinner, lighter liquids, and all the way from C10 to C14 or to C17, there are some going to be thicker liquids. Some books even quote the number such as C22. So it's really up to the books. Well, different isomers for these compounds behave differently. So there is not a hard and fast rule or a hard and fast boundary that you can draw over here. Because when we talk about, if I take any of these examples, let's say I talk about C16 alone, and C16 has thousands of isomers that we can discuss about. Some of them may be thicker, heavier liquids, some of them may be thinner liquid. It really depends upon the number of branches. So we do not draw hard and fast boundaries over there. And anything greater than C17, some books say C22, whichever number you put over here, are all going to be solids. Now remember, the first few ones, C17 to C22 or maybe to C24, are softer, waxy solids. And then afterwards, we have harder, strong solids, non-waxy or stronger solids, right? So if you remember this, you would automatically understand that C6 must be a liquid. Okay, I was repeating this point so that you get the point why we are taking hexane over here as a liquid. All right. So if you remember the prerequisites back from IGCSE, any of this should not be a problem for understanding portion. Okay. So I hope I have made my point by going for all of this. Now, moving on to combustion. Alkanes are often used as fuels. We burn them for many reasons. Generate electricity in power stations, heat our home, cook our food, energy needed for industrial processes, fuel for ships, airplanes, trains, lorries, buses, cars, motorbikes. It really depends upon different ranges. Okay, so that's not the main point. The main point is to talk about the types of combustion. Now, we are going to bifurcate into two types. We will discuss complete combustion over here. All of this is complete combustion. Now, back in ITCSC, we discussed this point that you can either produce carbon dioxide and water from this combustion. If that happens, you're going to cater it as complete combustion. This means this is going to give you more energy in the form of heat. It's a more exothermic reaction. Now, we usually come up with these balancing numbers. Remember, you can do it like this. Only the half fraction or zero point 0.5 are acceptable. 0.25, 0.75, 3 by 4, or 1 by 4 are not acceptable. Also, remember for this specific complete combustion equation, we went with something like this. Okay, so something like this was obtained. So based on this, I gave you the idea back in IGCSE to always first balance carbon, since the number over here and the number over here is pretty similar. That's really easy to just simply put this number over here. Divide this number by 2 and then put the number over here. It would be very easy to balance this one. And then x plus y over 4, divide this number by 4, add it to x and write the number over here. It's really extremely easy to balance these equations in a matter of few seconds and to get them right as well. Okay, so you can come up with a zero point 0.5 or a half fraction. You can even multiply the whole equation to write whole numbers over there. So I hope you get the point. Now, moving on to the next part, this whole thing is going to be incomplete combustion. Now, back in IGCSE, incomplete combustion was totally about producing carbon monoxide and water, but this time it's really going to be a step up because we are going to discuss it differently. Now, when the petrol or diesel is mixed with air inside a car engine, there is only limited supply of oxygen. Under these conditions, not all the carbon in the hydrocarbon fuel is completely oxidized to carbon dioxide. Some of the carbon is only partially oxidized since there is limited supply of oxygen. So we get to have incomplete combustion. We produce carbon monoxide, which is a toxic gas. I hope you understand that it bonds with hemoglobin in the blood. Hemoglobin molecules can no longer bond to oxygen and cannot transport oxygen around the body. So the victims of carbon monoxide poisoning will at start feel dizzy, then they would have headache, then they would lose consciousness. If not removed from the toxic gas, the victim would die. And that usually happens inside uh, in half an hour or less. So carbon monoxide is odorless, which adds to the danger. It was already colorless. It was already a danger itself. So this is why faulty gas heaters produce more carbon monoxide. Now, these equations aren't balanced in the same formula as the previous one, but the rule still stays the same. Try to balance carbon first, hydrogen after, and oxygen in the end. Since oxygen is bifurcated from one species on left to two different species on the right? Not just this, I'm going to move to the next part and explain a couple of points from there. Incomplete combustion can kill unsuspecting people in the room with poor ventilation. So, if ventilation is better, yeah, this may not kill human beings. But if there is poor ventilation, the chances of killing human beings are very much higher, especially when we use faulty gas heaters during sleeping. Okay. Now, apart from this, there are a couple of possible outcomes. This also produces sometimes pure carbon, which we call as carbon black, or which we may also call soot. This is usually noted in such a way that we may write it as something like this, plus H2O plus C. Now, with this kind of equation, it means along with carbon monoxide, we're producing water and we are producing carbon black or soot, the little black particles that tend to stick to any of the utensil or anything that we are using with incomplete combustion. They tend to accumulate on a surface. For this kind of equation, especially this one I'm talking about, two different students can come up with two different numbers and yet successfully be able to balance an equation. Usually, what we assume with chemical equations is that the numbers for the chemical equations are going to be the same for the entire planet, no matter if a teacher is balancing it or a student is balancing it. But there are some equations, as an exception, which can be balanced in multiple ways with different numbers, with different stuff. So in this case, it can be different. It is really up to the students how they balance it, right? These equations have been used rarely in past papers, but you should have the idea that this is very much possible, right? This is also known as incomplete combustion. Okay, moving on. As well as releasing carbon monoxide, road traffic also releases acidic nitrogen oxides because under high temperature and pressure in a car engine, exactly as the phrase is being used in IGCSE, you will use the same phrases in AS and A level that it can produce NO and NO2. Now, this contributes to the problem of acid rain. Acid rain can kill trees, aquatic animals in lakes, or you can say the whole aquatic life. It's not just the animals they kill the plants as well. They destroy the whole aquatic life. Now, acid rain can erode limestone buildings, statues, metals such as iron and other metals, which can get eroded easily. So in normal combustion, nitrogen gas in the air is not oxidized. However, at high temperatures in car engines, as I just told you, or under high pressure, this may happen. N2 and O2 can react to form NO, and upon further oxidation can produce NO2. Now, the vast number of cars on the road pollute our atmosphere. Nitrogen oxides from the traffic contribute to photochemical smog as well as acid rain. So, toxic carbon monoxide, acidic nitrogen oxides, unburnt hydrocarbons, and that sometimes cars release. Remember, hydrocarbons are commonly written or abbreviated as HCs, unburnt HCs, or volatile organic compounds, which are abbreviated as VOCs. They are all pollutants, be it primary pollutant or secondary pollutants, they are all pollutants. Remember, the pollutant that is produced directly or as a first product is known as a primary pollutant, and then the pollutant which is produced after the reaction of pollutant themselves are usually known as secondary pollutants. So it may be one of the options. Okay? Some of these are carcinogens, they can cause cancer. This also forms PAN for acetyl nitrate, right, which is a contributor to photochemical smog. We have discussed it previously in chapter number 13, the chapter with nitrogen. So let's keep moving on. Reducing traffic emissions, what we do is that we usually fit the motor vehicles with catalytic converters in their exhaust systems. So what the catalytic converter tends to do is that it oxidizes carbon monoxide to carbon dioxide. This is written in words. You should be capable of writing an equation about it, right? Or the reduction of carbon nitrogen oxides to harmless nitrogen gas, which was very much possible because of the reaction like this. Okay, so the oxidation of unburnt hydrocarbons to form carbon dioxide and water, which could be anything like this. Now, if you look at your left-hand side, the reactants in the equation, you'll find some gases which are problematic ones, either toxic or the reason for acid rain or photochemical smog or other environmental pollution problems. But on your right, you'll find the gases which are usually already a part of the atmosphere. They still might be problematic gases, but less problematic ones. Okay. So unfortunately, catalytic converters can do nothing to reduce the amount of carbon dioxide or greenhouse gas given off in exhaust of cars or trucks. I hope you get the point. Now, don't forget the structure of a catalytic converter, which can work. Remember, precious metals such as platinum or rhodium or their alloys are used in a honeycomb structure to provide a large surface area on which these reactions can occur. So, a side view can give you the idea. I've already completed these equations, so this shouldn't be a problem. Okay. Moving on. Substitution reaction of alkanes. Now, we have studied them previously, but this is the point where we dive deeper and we are going to discuss the details. And since I've already discussed the details of substitution reaction, apart from that, the free radical mechanism with initiation, propagation, and termination steps. So now we are going to discuss all of this in a combined detail. So alkanes undergo substitution reactions in sunlight. This may also happen in simply UV light. Uh, Few of these reactions also happen under high temperature conditions, right? So sunlight actually provides the necessary energy to break down this chlorine molecule into chlorine free radicals, which are very reactive and actually start the whole reaction. So talking about this reaction, a hydrogen atom in an 10 molecules gets replaced by a chlorine atom. We call it substitution. Remember, since this is happening in sunlight, these are also photochemical reactions, but they actually fall under multiple categories of reactions. So what role does the sunlight play? I hope you get the point. I've already explained it. Moving on to the initiation step. This is the first step. Since I've already written this step and explained it in the previous portion, the initiation should not be a problem. Yeah, but as distant as you may see the dot in the book, this is a typo error. So make sure you put it right over here, right? On the top right hand side, not next to it. That's not the way you do it. Okay, moving on. Okay. Hexane and bromine mix and leave in sunlight, mix and place in a dark cupboard gives you a very good idea. Now, reaction to give a mixture of bromohexanes and bromine color disappears, and the bromine still has its color, gives you an idea that the reaction is going to happen in sunlight and will not happen in dark. But that only goes for chlorine and bromine. Remember, in the halogens chapter, we discussed that fluorine is so reactive that it does not even need a broad sunlight for this reaction to happen. If it does, the reaction is explosive. The reaction may also occur in diffuse sunlight, or sometimes the reaction occurs in dark if conditions be probable. So we are just talking about chlorine and bromine. We'll be only talking about safer reactions. We talk about bromine because these reactions are safest for school labs. Even in sunlight, bromine does not give us an explosive reaction. So this can actually be done in school labs. Now, as soon as the chlorine-chlorine bond breaks, each chlorine atom takes one electron from the pair of electrons. And I hope you understand the homolytic fission that we discussed previously. That's how they form free radicals with unpaired electrons. Now, the propagation step. Free radicals are very reactive. In this specific case, take a look. We're talking about ethane, chlorine free radical. It forms a radical, and hydrogen comes out of it to react with this one. And that's how this happens. Now, I hope you understand that this actually works this way. I'm going to explain it. I want you to make sure, I want to make sure that you get the point. Now, we have this. Now, one of the bonds are going to break homolytically. Remember, you always show them with half arrows, fishhook arrows, I mean, but not both at the same time, one pointing towards one another, another pointing towards another atom. Now, I hope you understand that hydrogen comes out of it not as positively charged, but as a free radical. And these two actually combine together to form HCl. So much so that we're going to have a single bonded HCl molecule and we are going to have a CH2, CH3. And since we're going to show the free radical, you'd notice the dot on carbon, not on any of the hydrogens. And it has to be the exact carbon. So the carbon which has one hydrogen atom less, that carbon is actually the base for the free radical for this whole molecule. So just writing this molecule, drawing it over here, drawing it over here, drawing it over here, all of these are going to be wrong. It has to be on this carbon atom. That's what that's what makes organic chemistry more systematic, but at the same time, it makes it more difficult because you need to be vigilant even withdrawing the simplest and smallest of things like a dot. All right. And I hope I've made myself clear when I say it like this or put it like this. Okay. In this propagation step, what's going to happen is that a CH bond in CH3 broke homolytically. I've already drawn this for you. An ethyl free radical is produced. Now, this can then attack a chlorine molecule, forming chloroethane and regenerating a radical. Now, a radical, um, Saad is not here today, but he asked me a question that day, which I never completely explained, and I actually intentionally kept it. So at this point, if we talk about this one, and I'm giving you an example in order to answer that question. That notice he's calling it an ethyl free radical. Now, as soon as we convert it into a radical, of course, we're going to take a hydrogen atom out. In the similar way, we name the entire alkane if the hydrogen was a part of it. In the similar way, we simply remove that hydrogen, we convert it into YL, an alkyl radical, so we name it accordingly. So my basic point, which I said as a part of my answer on that day, remains the same. The rest that I kept intentionally for answering now, I've explained it that that's how we name it. This is a very good example giving you an idea how we name the alkyl free radicals. So whatever that is would be named accordingly. For example, if this is butane, if you take hydrogen out of it, this will become butyl free radical. And this is an isomer of butane, which is usually named as 2-methylpropane. So it would be 2-methylpropane radical. Okay. So the radicals are named according to the original compounds, as if the hydrogen was a part of it. We would name it. We'll name them in the same way, just that the alkanes are then named into alkyls. And that's how the radicals are named. I hope this also clears about the example. But any structure bigger or more difficult usually does not come as a part of A level, so it should be easy. Moving on, propagation step can be repeated as the chlorine-free radical can attack another ethane molecule, since you have the same thing by the end of propagation reaction, which gives you an idea that propagation reaction would always be a two-part step. Notice in the first part, ethane plus chlorine free radical or gives us the ethyl free radical and HCl. The ethyl free radical then reacts with the chlorine molecule, giving us ethyl chloride plus a chlorine free radical. This chlorine free radical can then again attack an ethane molecule. So I hope you get the idea that the propagation would always be a two-part reaction. Notice in both the parts, a molecule reacts with a free radical to produce a free radical and a molecule. Radical plus molecule, molecule plus radical. It gives you the same thing. That's how propagation reaction goes. Okay, so it is going to be really easy. I am just keeping this right now as a part of an explanation, but at the end, when I'm going to summarize it, this is going to really help you, because if I put it all of this together, the way I was saying it, it would make much more sense to you. So I'm going to keep it for a few more minutes before I get to the end and explain this. All right. So moving on, the word propagation usually refers it to growing new plants and mechanism. The substitution reaction progresses. It's type of a chain reaction. It goes on and on since the radical is generated by the end of the two-step reaction. So I hope you get the point of using the word propagation. Now, this reaction is not really suitable for preparing specific halogen because we get a mixture of substitution products. This is a very good point. This point was explained very briefly in IGCSE, but here they're going to add in some more details that you get a complete idea about it. For example, the example is put to make sure that you get the whole idea about it. Ethane and chlorine react. Now, the product may include different chloralkanes. This can include 1,1 or 1,1,1, 1,2 or 1,1,2 or 1,1,2,2. Remember, all of these are possibilities, and so on. So, as well as chloroethane. So, it gives a really good idea that we can have a single chlorine based product, or we can substitute two hydrogen atoms out of it, maybe three, maybe four, maybe five, or we can eventually it can replace all the six hydrogen atoms so much so that we get hexachloroethane at the end. So it really depends upon how long or with what kind of condition the reaction goes, and we can have different products, which means we cannot target a specific halogen alkane by doing this. That's not how they are prepared. Since this point was all uh, explained back in IGCSE2, but with just one or two sentences, with these kind of namings and with this kind of idea, I hope you completely get the point that how many different kinds of alkanes are possible. And really, a lot of alkanes are going to be, halogen alkanes are going to be possible. Remember, number of hydrogen atoms, the more the hydrogen atoms you have in a compound, the more would be the number of possible outcomes of halogen alkanes you're about to get. So with methane, four different chlorine products are possible. For ethane, there are many different products, not just four, not just six, much more than that. So if the number of hydrogen atoms keeps on increasing, there are a huge variety of fluoroalkanes that you can produce. Okay. So for example, take a look at this and followed by this. Now, this example is specifically given in the book that this is possible as a question in papers. So it is giving you the idea that we can have a product with a single chlorine atom per molecule, or may have a product with two chlorine atom per molecule. We may have more. It may contain three, it may contain four. Now, you should be capable of adding more chlorine atoms to it as per the examiner demands. Okay, so this gives you the idea. I hope you are good with this one. The more chlorine gas in the reaction mixture to start with, the greater the proportion of chlorine atoms in the chloroalkane molecule are going to form. Okay, moving on, termination steps. Now, when two free radicals meet, they will react with one another, and a single molecule is the only product. Now, this gives you a very good idea. Can you give me a minute? So, termination step. Before I really start explaining the termination step, let me just give you a little bit of a summary. Now, if you look at it, the steps have a very good systematic sequence. The initiation, a molecule is converted into radicals. Usually one molecule is converted into two radicals. If you look at propagation, although propagation was composed of two steps, but really both the steps had the same symmetry. Molecule plus radical gave you molecule plus radical. Okay, and the termination step was all about radical plus radical, or as a whole, radicals would give you a molecule. So if you look at it, molecules give radicals or radicals give molecules. Initiation and termination are exact opposite to one another. This should give you a very good idea, a very good mind map in order to how to start on with writing the equations whenever you're faced a question like this. So use a molecule such as Cl2 can be converted into 2Cl radicals, and you can write the exact opposite. 2Cl radicals can give you a Cl2 molecule. So the initiation and the termination steps are exactly opposite to one another. Okay, but since not just this, any of this is possible, so the termination can be anything. Termination can be something bigger. What do I mean by it? Take a look at this. Ethyl radical plus chlorine radical gives us ethyl chloride, or maybe two ethyl radicals can react to form butane. That's even possible. Okay? So since we are discussing the possibility about this, I hope you understand what's going on in the whole process. It's just that the propagation goes on as a chain reaction. Why do I keep saying the propagation goes as a chain reaction? Because one single chlorine free radical, when we talk about ozone layer and when we talk about that they are destroyer of ozone layers, as I discussed in my previous examples, is capable of breaking this many ozone molecules before the radical even goes for the termination process. So do not think that it's a complete progression and the reaction goes always in this kind of direction. Remember, initiation happens and propagation goes on for a longer duration of time with so many reactions. Take a look at this example, and then comes the termination part in real life. If I talk about ozone example, this is a very good way of explaining to the student that this is not going to happen in just three steps. There you go, boom, the reaction completed. That's not how it goes. That's why we keep using the phrase chain reaction because propagation goes on for long. So one chlorine free radical is capable of reacting with 10 raised to power 5 ozone molecules, or simply speaking, 1 lakh ozone molecules before it can go on for termination. I hope this gives you a pretty good idea of what's happening. Okay, so the same thing is explained over here. This gives you a very good idea. So overall, the reactions between alkanes and halogens involving initiation, propagation, and termination are all known as free radical substitution. So wherever you see this word, this automatically means that there are three steps following one after another. So whenever free radical substitution, this term is mentioned, the examiner probably wants you to go ahead and discuss any of these three steps. Now, whatever the examiner asks you, you need to answer him accordingly. He may not ask you the whole thing in progression. He may not ask you to write the initiation, propagation, and termination reactions. He may ask for any simple reaction for 1 or 2 marks, and that's about it. He may not go with an entire progression. And you would see the same examples in past papers. So that's why you are told in such a way that how you can write simply one example for a reaction so that you don't have to get started with the reaction top and you go with an entire order. Even if you can break the order, you can simply imagine what's going to be in the progression reaction alone or termination reaction alone. And this gives you a very good idea about it. Moving on. Okay.